I got to wait for him?
Yeah.
Oh. All right. Good afternoon. I'm Adedeji Oduwole. I simply go by Deji. I found out my first name is too hard to pronounce. I'll be talking about satellite collision alert for space situational awareness. My partner is not here today. He had to be out of town. But without my partner, we wouldn't be here right now. He did an enormous work for this presentation to have taken place. He did a lot. I'll put it that way. All right. Our goal is to basically protect objects that are in space, from GPS to military satellites and stuff like that. So I get lost a lot. So this was actually a good fit for me. This is basically what I just said. There are a lot, like space, how would I put it now? But space, innovations in space travel and stuff like that has expanded over the decade and over the last 5 decades. Like since the first man landed on the moon to now, there are numerous satellites in space that have to be tracked and stuff like that. So this is actually a growing field for electrical engineers. Now, we have problems with tracking. For example, there are different types of satellites. There are certain satellites in space, they are no longer in use, and for example, it may be too costly to retire them, to go ahead and dismantle them or make them explode and stuff like that. So those are the derelict satellites, the ones that are no longer active. There are satellites that are cooperative, like satellites say all GPS systems actually let everybody know, where they are. But there are certain satellites that are of national security interest. Or say China, for example, won't let the United States, for example, know what's going on with their satellites and stuff like that. So it has different dimensions to it. Space is a world on its own. Now, the goal of this project, like I said earlier, is to determine the probability for satellites to collide. For example, we know the trajectory and the position of satellite A, and we know the trajectory and the position of satellite B. What is the probability that these satellites will collide at any point in the future, based on their known trajectories, provided that nothing happens to them and we don't know that. Different things cause change in trajectory. For example, whatever we worked on right now wouldn't work if the orbits of each satellite change, of any of the 2 satellites. For example, we're using Kalman filters and stuff. We basically saying we're predicting what's going to happen in the future. If what we predict in the future is way off what actually happened, then we're in trouble. We just predicted something that is absolutely off mark. Our covariance and everything it has no meaning to it. And like this slide points out, like we did in our first presentation, different things cause change in the orbits. For example, station keeping intentionally. A station, for example, may change the orbital elements of a satellite without us knowing. Orbital transfers, you increase at certain points, if we could increase the angle of perigee and stuff, and the satellite changes orbits, goes into a different orbit, if we put more force to it. And then unintentional orbits, tugs, anomalous gravity, we all took physics 1 and stuff like that. We know that the gravity of the Earth is not constant at all places around the Earth, so that may cause changes in the orbit of a satellite. Now, to the studying in the body of what we were doing, like I mentioned earlier, we use Kalman filters. We use the uncentered Kalman filter as to the extended Kalman filter, because the uncentered Kalman filter has an advantage over the extended Kalman filter in our application. Basically, what we do is we have a measurement. We know state A. We predict state B. Then we go ahead and measure state B, and then correct our measurements. So we keep going like that from one state to the next. Like I explained right there, the UKF does. It just uses the state. It measures this state. Like I'm here right now. I know this state. I predict the next state that I'm going to be. Then after I move to that state, I measure I take measurements of that state to be able to predict the next state. Two-line elements. For example, there are coordinate systems that we are familiar with. Familiar with the XYZ, the Cartesian coordinate system. We're familiar with the spherical coordinate system. We're also familiar with the cylindrical coordinate system. But in our application, we use what is called the two-line elements. That's what tells us the position of any celestial body at any point in time. The satellite readings, the readings by satellite monitors are not taken in forms of the Cartesian and other coordinates we use. They're taken in form of two-line elements, which have 6 parameters, which I'll be talking about later. We convert these two-line elements into what we can use, what we're familiar with, what we can actually perform calculations on, which is the Cartesian coordinates, to the Cartesian coordinates for our speed and position. And this is a snapshot of a code written by my partner that takes the two-line elements I was talking about for 2 different satellites. TLE1 is two-line abbreviation for TLE1 is two-line elements for one. These 2 are two-line elements for one satellite, and this pair is another two-line elements for another satellite. So, because we're tracking 2 satellites, and this function basically converts these strings into two-line elements in numbers, and then back into the Cartesian coordinates like we know, like we can work with. So, like this is basically what I described. This is a celestial body, say satellite A. It has 6 different parameters that are associated with it. We have the orbital inclination. We have the right ascension of the ascending node. It's not shown in this diagram over here. We have the eccentricity. For example, if you took in calculus 1, we talked extensively about eccentricity and stuff like that. A circle has an eccentricity of 1. A parabola has a different eccentricity. An ellipse has a different eccentricity. So this is what the trajectory of any satellite is falls into a particular eccentric classification. And then we have the element set approach in the mean motion. So these 6 parameters determine the position of any satellite at any point in time. It's these 6 parameters, like I mentioned, that we convert into Cartesian coordinates for use in our trajectory projector and stuff like that. And like I was explaining earlier, like this is a MATLAB code, a snapshot of a MATLAB code that does the prediction, the update, and the measurements and stuff like that. Right here is the beginning of the code. This is our initial state. Like I said, this is point A, and I'm going to predict point B. This right here uses Keplerian, it uses Kepler's laws to project the orbit and differential equations and stuff. So we project the new position and the new covariance, and because P1 is the covariance of our prediction, the error in our prediction, and then we update right here, and then go back through the same thing over and over for both satellites. And after that, now we can project where the satellites are going to be. The thing is, then the question is, what is the probability of them colliding? Since we now know where it's going to be in the next 10 seconds, we can predict with a degree of accuracy where the satellite is going to be in the next 10 seconds. What is the probability of it colliding in the next 100 seconds? Using what we know. And so we basically used the UKF, like I mentioned earlier, to do that. Like I put in that slide, there's a basic scenario you could actually follow right there. That I think I skipped over that. This problem has 2 different satellites. I skipped over something very important. We have the LEO and the GEO satellite. The LEO satellite is the lower Earth orbit that tracks the other satellite that is further away from the Earth, is in the geosynchronous orbit. So one LEO satellite, like I said, lower Earth orbit, revolving around the Earth, tracks 2 different satellites. At one particular point in time, there's going to be a problem. The Earth is going to be on the way of this LEO satellite that is revolving around it, and it's not going to be able to track. It's not going to be able to take measurements of these other 2 satellites. And then, the longer the Earth is in the way, the higher the degree of inaccuracy in our measurements of on our prediction, there's a cone around the geo satellites that it may be wherever in that cone of error. So basically, we followed, and in our first presentation, my first idea was to use the probability density function, the PDF of both satellites to predict to use, but I found that was inefficient. I was messing around with the error function. It was giving me something really wonderful, but not right. So like I said, I don't. This is basically what I went into the slides a little bit further. Like, this is the method, the probabilistic method, the steps I followed to design this probabilistic method with the help of Dr. Chen. We used Kepler, the Keplerian orbit, to propagate, where is it going to be in the next 20 seconds using our Kalman filter. And then we measured the distance between the relative distance between satellite A and satellite B. And is the difference of this distance less than what we actually want, like 10 kilometers, which was what we were actually working with? Is it less than 10 kilometers? If it's less than 10 kilometers, what's the probability of them colliding and stuff like that? Okay. If the probability is greater than 40%, we give an alert that shows up. There's an alarm. These two satellites have a further probability of colliding. And this is the MATLAB code that does the probability. Like we all know, the probability equation says the number of occurrence of an event determined over the total number of sampling. The sampling is n, and count is the number of occurrence of an event. So if this is the position of satellite A, I should use this. This is the position of satellite A and the position of satellite B. We take the relative distance between both of them, the including distance. Is it less than D, which we specify to be 10? How many times does this occur? And at the end of this occurrence, do the probability, which is the number of times of occurrence over the entire sampling period, which is the probability. And if this probability is greater than 0.4, alarm the service center. If it's not greater than 0.4, if it's less than 0.4, we don't care about it. It's not so much of a problem. And basically, this is what I was working on, but I couldn't get. I was still working on this. Each time, because it's in a loop, each time it does the time in the future, and the probability of collision is this at this point, and the minimum distance between them, you can actually see it keeps writing over. It keeps writing over the same. The first thing is reading before, at the end of the loop, which is very long. This is all dark. Like, you can't even read whatever I wrote in there. And like I was saying earlier, this is the LEO satellite, the lower Earth orbit satellite, and these are the two geosynchronous satellites. We can say the Earth is right here, and this is the orbit of this one. There's a video next. I hope this plays right quick.
I think you need a video file if you want. If you only insert the link to your PowerPoint slide.
I uploaded the video.
Okay.
And they said it was supposed to play automatically.
Maybe I can try to click.
Yeah.
On
It's not going to play. But basically what that video contained was these two satellites going in their respective orbits around, and this satellite was also moving around the Earth, monitoring to these two satellites. I was going to use that to show the cone of uncertainty of our measurements as the Earth became a block in the way of the measurement. And that doesn't play. And basically, what we intend to do in the future, I won't be here this summer in REU, so I hope, and my partner won't be here either. So I guess the new people that come in for REU, we're trying to extend. We worked on two satellites. We're trying to make this work on n number of satellites. Can we monitor 100 satellites and be accurate in our, which we call it, our observations and calculations and stuff like that. And applications, defense, GPS, stuff like that. nice stuff. And bam, references. And thanks to Dr. Chen, first, we won't be here. He was a lot of help, which I appreciate that. He has extensive knowledge in the field, and he was willing to give that to us and help us out. And thanks to Dr. Dimitris for the REU, and thanks to everybody, my colleagues and stuff. And thanks to the audience, too, and thanks to the NSF for paying us. Any question?
Have you been following in the news where they have a rogue satellite right now?
No.
There's an Intelsat satellite that's awry, and it may interfere with cable television because it's going too close to another one.
And if you made this work real well right now, you could make $1 million.
Yeah, right. You could be tracking that satellite.
I wish I had the resources to do that. Yeah. Quick way to make money, I guess. Any other questions?
I think if you have your video file on your flash memory, maybe you can directly play that instead of clicking on the PowerPoint.
Maybe skip the PowerPoint.